Good morning, everyone, and thanks for coming. And also, I would like to thank the organizers for giving me the opportunity to talk about this recent work about achieving Heisenberg limit in quantum metrology using quantum error correction. And also, I should thank Raphael for the very nice first part of the talk yesterday. And this will be kind of like the second part, which is the other side of the coin, tells you about how quantum error correction are going to assist metrology. So as we know that in the past few years, there have been lots of excitement in both fields in quantum metrology, where like LIGO has detected the first events, and also there are lots of developments in nitrogen vacancy, magnetometers or other applications, and also atomic clocks, and so on. On the other side, we also have the quantum error correction, which people have been working on it for many years, and there are different error correcting codes has been invented and applied for different types of errors. And one of the achievements which I would like to highlight is actually by my colleague Rob Shokov. And in 2016, there's a work which demonstrates that we can correct boson loss errors and achieve something called the break-even point, so that using a specifically designed bosonic error correcting code, you can correct boson loss errors and do something with error correction, so that actually you can do the performance of the scheme with error correction is actually as good as the best scheme without error correction. So that's what we mean by the break-even point. And this is actually the first and so far the only experiment which demonstrates the break-even point. And in addition, there are also other error correction schemes based on ions and nitrogen vacancy centers or superconducting qubits. And so both fields have made a significant development. And one natural question is, actually, is it possible to actually apply some of the quantum error correction techniques to quantum metrology so that we can build a better sensor or have the benefits from the error correction? So that's actually the key motivation of this research. And so in the next 35 or 40 minutes, I'm going to basically briefly review the quantum metrology and set the stage for quantum error correction and give an example of quantum error correction assisted sensing. It's just a single 1 qubit, 1 ancilla example, and then give a general criterion for conditions needed to achieve a Heisenberg scaling with quantum error correction, which is, I'll explain what is the Hamiltonian not in Limblad span criterion. And with that, then I also like to give an example of another example of error correcting codes that can be used for sensing. So first, what is the goal of quantum metrology? So we want to estimate a parameter or a few parameters of a quantum system. And for example, it could be the energy splitting of a two-level system, and due to external magnetic field and so on. And one key feature of quantum metrology is actually use the quantum coherence, which is the superposition, a coherence between two superposition states, so that you can actually continuously accumulate a phase that allows you to achieve something called the Heisenberg scaling. And the one simple example to see it is actually to look at something called the Ramsey experiment. And it's pretty standard textbook example. So let's consider just have a two-level system which has a Hamiltonian which is proportional to sigma z with a proportion coefficient omega. And we want to estimate the frequency omega. And one way to do it is to start from a state which is a symmetric superposition of 0 and 1 of the two-level system. And we let this state evolve under this Hamiltonian for some time t. And after time t, the system will evolve into a superposition of 0 and 1, but with a slightly different relative phase between the two components. And then we measure the probability of this state projected to some other state. And that probability will have an oscillation which scales as omega times t. So as you see that the longer the time you wait, the faster the oscillation with omega. And you will see that after total time t, the capital T, then you will have a sensitivity of this omega, which scales inversely with the capital T. And this inverse scaling with 1 over capital T is actually here what we mean by the Heisenberg scaling. And this seems very natural as 1 over T, but just in contrast to the typical classical average schemes, what we usually do in the classical world is that if we have long enough time, we're going to repeat the experiment n times, where n will be just the capital T divided by tau, where tau is the duration for each experiment. And due to central limit theorem, the variance of this quantity, the standard deviation of the quantity measured scales at 1 over square root of n, and proportional to 1 over square root of t. So here is a contrast between the quantum and the classical. And as we see that in the quantum case, it has a more favorable scaling, so that with a given long duration amount of time t, we actually get 1 over t scaling in terms of the uncertainty, which is an advantage compared to the classical case. However, in practice, they will never live in an isolated world. There will always be decoherence going on. And here, maybe before moving on, the key message is that if we have unitary evolution, basically we can achieve the Heisenberg scaling. So in the real world, we actually will have decoherence, such as dephasing or spin flip noise. And if we want to do that, if we follow the same procedure as we outlined earlier, we prepare a symmetric superposition after interrogation time, actually it will not evolve to a pure state, but to a mixed state. And the key difference is the off-diagonal term of mixed state will have an exponential decay. And then if we do the measurement with overlap to some certain states, we find that the oscillation decreases exponentially with this typical decay rate. So basically, due to the decoherence, then the earlier protocol will not work. We cannot wait for arbitrary long time, because the longer we wait, if waiting time is longer than 1 over gamma, then the contrast will be vanishingly small. So that's why actually the optimum choice of the waiting time for the interrogation time is scales roughly as 1 over gamma. And that optimizes sensitivity. So if we have a long duration of total time t, then we actually need to repeat the experiment capital N times, where n is roughly gamma times t. And then we actually go back to the classical limit case, which sensitivity scales at 1 over square root of n, which is proportional to 1 over square root of t, which go back to the classical scaling. So basically, in the presence of decoherence, it prevents us from achieving the Heisenberg scaling. And now there's a question, which is how can we actually restore the Heisenberg scaling in the presence of decoherence? And so in order to answer that question, let's make a more formal formulation of this problem. So basically, we have two parts in this formulation. One is the Hamiltonian part, where here we assume the Hamiltonian is proportional to some generator with the proportionality constant being the parameter we want to sense. And also, there is a dissipative part, which is characterized by these jump operators. And we allow multiple jump operators. And here, we actually assume that the noise is actually a Markovian noise, which in some sense is the most detrimental noise. Because if we have a time-correlated noise, maybe there are some even simpler techniques like a spin echo to suppress those things. And here, we actually intentionally to consider the most adversary type of noise, which is the Markovian noise. And the dynamics will be characterized by this Limblad master equation. And for the discussion later on, we actually will be mostly interested in a small duration evolution with time dt. And then the evolution of the system will be characterized by this quantum channel with epsilon dt. And for small dt, we basically just need to expand the evolution up to the linear order of dt, and we can ignore all the quadratic order of dt's. And we can collect all the terms. As we know, the quantum channel will have a cross operator representation. And here are the cross operators, capital K, subscript little k. And so there will be a dominant part of the cross operator K0, which is basically identity with some correction associated with the Hamiltonian and this Limbladian to make sure it will be normalized properly. And the interesting part is that there will be this additional noise jump operator induced cross operators, which is proportional to the jump operator, and there is a square root of dt to be associated with the duration of the evolution. So basically, we translate this master equation to the quantum channel with the cross operators, something correction to identity, and also something which is proportional to the jump operator. And this is basically the setting of the noise model. And in terms of the scheme, we try to use error correction to help quantum metrology. The scheme we'll consider is actually you can think it as a special case, as what Raphael talked about yesterday, which is you can view it as a sequential scheme. So in case you were not here yesterday, the sequential scheme is basically you have one probe with many ancillas. You initialize the probe and ancilla, and then let the probe for duration dt. And then you use the ancilla probe combined system to do some control operations. And then let the probe acquire information for duration dt, and then do operation over the probe and the ancilla, and repeat this procedure many, many times. In the end, you do a total measurement of the system. And this is actually, in some sense, it's actually the most general scheme that you can come up with, because any other protocols, like parallel protocols, you can actually envision it as the probe with these ancilla, and these controls are basically doing the swap operations between your probe and ancilla, so that you can do the parallel scheme. And the preparation could be some entangled states being prepared. And but for our purposes, actually, with the error correction protocol, we basically need to consider a special case of these controls. So first, this small acquisition time allows us to accumulate the signal, while the control part, we actually mostly consider doing quantum error correction. So we have lots of ancillas, and here we assume these ancillas are noiseless, and they're initialized to some fixed state, which has a low entropy. So basically, by coupling the probe with the ancilla, we actually would like to achieve something which is to use the ancilla to extract the entropy from the probe and induce a coherent unitary evolution within some logical space of the probe and ancilla system. So that's actually the key part, which I'll discuss more as what we will do in this control part. But the whole scheme is actually very simple. It's basically the sequential scheme with stroboscopic evolution, consists of signal acquisition and quantum error correction. And the goal is basically we want to induce an effective, pure unitary evolution within the logical space so that we can achieve Heisenberg scaling. So that's the key idea. But now let's actually consider some examples before we give the general formalism. So the first example is actually consider the qubit probe with spin flip sigma x jumper errors. And this example is actually was conceived by 4 papers simultaneously in the year of 2013. And the idea is the following. This is a setup. We have the Hamiltonian, which is proportional to the spin Pauli Z operator. And we have this jumper operator, which is Pauli X. So they are orthogonal to each other, or at least not parallel to each other. And then generally, if you don't do anything, actually the system will decohere, and you will not be able to achieve the Heisenberg scaling. However, these authors from these papers, they propose that actually let's introduce an ancilla, which assumed to be good. And then we can prepare something called a quantum like a repetition code, 0, 0, and 1, 1. These will be the logical states, consists of the probe and ancilla. And just to keep in mind that the probe may suffer from decoherence, but the ancilla is actually noiseless. So if there is an error happen, it must be the error happen to the probe, which will flip the probe. So the 0, 0 will go to 1, 0, and the 1, 1 will go to 0, 1. And here, actually, just a simple 2-qubit repetition code is already sufficient to correct this error, because we know the error only happens to the probe. So basically, what we can do is to compare, to measure a collective quantity, which is Pauli sigma z of the probe and ancilla. If it's equal to +1, it means they are the same. We don't need to do anything, because they will be in the logical space. If they are opposite in sign, we will get this operator being -1, then we can flip the probe to restore to the original logical space. So basically, this simple repetition code allows us to correct bit flip errors. Moreover, actually, this code not only can allow us to correct bit flip errors, but also allow us to simultaneously sense the signal, which is the Pauli sigma z. The reason is that for these 2 code words, they will evolve differently with a different phase accumulation under this Hamiltonian. So now let's consider the detailed protocol for sensing. So we can start from a symmetric superposition of these two code words, C0 and C1. Okay, now notice that this time the code words consist of both the probe and ancilla. And we let it evolve under this Hamiltonian. So after a small interrogation time dt, there will be many possibilities. There's no jump, one jump, two jump, and so on. But basically, we can ignore those cases with two jumps and more because they are of order gamma dt square. For dt small, we can ignore those high order effects. So we only need to focus on the case with no jump or one jump. So if there's no jump, basically we have a coherent evolution with the states that evolves as a phase as it should be. And this occurs with the probability of order 1 minus gamma dt. We ignore the quadratic terms. And if there's one jump happen, basically you will go from the code space to the error space. So basically it will be evolving to a state which has a C0 prime and C1 prime. And since the one jump is already of order gamma dt, all the other corrections will be higher order in terms of gamma dt. So effectively, for the one jump, it just evolves into the error space with the corresponding same phase accumulation. Then after the error correction, we can map these error space back to the code space and add these things up. So basically, we restore the coherent evolution in the logical space up to some quadratic correction. And for small dt, we can ignore the quadratic correction, and basically we recover the unitary evolution within the logical subspace. So that's the key idea. And then if we let it repeat many, many times, then we basically can get the unitary evolution with the total time capital T. And we basically restore the Ramsey experiment in the logical space, which gives us the Heisenberg scaling. So this is basically the key idea. And actually, later on, you will see the general case, which actually this thing kind of like shows up. The underlying idea is exactly this protocol. So far, we only look at the one example, which has this dissipation, which is not parallel to the Hamiltonian. So let's look at another example. If the dissipation is actually parallel to the Hamiltonian, then in this example, actually there is no way to achieve the non-trivial unitary evolution in the logical space. And at least these papers, they didn't talk about it. And the one thing I should point out is that there was an experiment which also demonstrates the previous example. And for this example, there is no protocol to overcome this decoherence. It's because you can try, if you do repetition code like this, then you cannot correct sigma z jump. If you do repetition code like that, then you can correct the sigma z jump, but also at the same time you eliminate your signal, because the signal will also be identified as the error. So basically, for this case, when the signal and the noise jump operator, they kind of parallel to each other, then the quantum error correction cannot distinguish whether you are getting the signal or you are getting the noise. So either kill them all or just left the noise uncorrected. So, and there was actually, I should put another reference here, there was actually another nice paper by Sadetsky and others which prove that actually in this case it will not work. Yeah. So now we're actually like ready to get to the more general case, which is, and we want to figure out under what condition the quantum error correction can help to restore the Heisenberg scaling in the presence of decoherence. And the statement is actually the following. It's called the Hamiltonian not in the Lindblad span condition. So first, we have these Hamiltonian and the Lindblad, which is the setting of this question. And once we have Lindblad, we can define the span associated with identity, Lindblad, and actually here I should add the Lindblad Hermitian conjugate and the product of Lindblad with its Hermitian conjugate. And here, and actually what's the relevant part is actually the span associated with the Hermitian part of these operators. And that will give an operator space. And then you ask the question if the Hamiltonian, the generator for the Hamiltonian, is whether it's in that operator space or it's not in that operator space. You'll get yes or no, right? If it's in the operator space, then the statement will be it will not we will not be able to achieve a Heisenberg scaling with error correction. If it's not in the operator space, even though there's a tiny bit of this generator which is not lying in this operator space, then we could actually use that additional tiny bit which is not in the operator, this Lindblad span, to actually achieve the Heisenberg scaling in sensing. So let's just check the examples that we already had. So if we have the probe with a sigma z jump, which is actually the noise which actually we cannot correct them, is actually the span consists of identity and sigma z, while the generator is sigma z, so the generator is within the Lindblad span. So basically we cannot design error correction scheme to restore Heisenberg scaling. On the other hand, if we have sigma x jump, then the Lindblad span will be identity sigma x, and when you have a sigma x stagger, sigma x gives you identity, so basically it's spanned by identity sigma x. And in this case, the sigma z is not in the Lindblad span, and we can actually design the error correction to achieve Heisenberg scaling. So these are just the two examples that we discussed earlier to show that it's actually consistent with this condition. But now let's actually check, okay, why this theorem is true, and the proof basically consists of two parts. The first part is the necessary part, which says we need this condition in order for the Heisenberg scaling to work. And this is actually detail discussed in Raphael's talk yesterday, but in just a one-line summary, is basically we can choose the gauge so that the cross operators can be chosen in such a way that we can bound the quantum Fisher information as something which scales linearly with time. And once we have this linear scaling, then we can infer from that we can bound the uncertainty which scales as 1 over square root of t. So that gives us the standard scaling, which will rule out the possibility of Heisenberg scaling. And the new part, which is Raphael advocated, like we will discuss more, is actually the sufficient part, which is if this condition can be satisfied, we can actually come up with an explicit procedure to create a quantum error correction code that allows you to achieve the Heisenberg scaling. So that's what we will discuss in the next 2 or 3 slides. So just keep in mind that we have this generator, which here we want to show the sufficient condition. It basically we want to show if the generator is not in the Lindblad span, we need to come up with a quantum error correction code that allows us to achieve the Heisenberg scaling. So let's just think, what do we mean? What can we say like if it's not in the Lindblad span? Geometrically, you can think that there is some component of the generator which is sort of orthogonal to the space associated with the Lindblad span. And that's actually the orthogonal part that we're going to use to construct the quantum error correcting codes. Okay, and just make sure that everywhere on the same page. So here's just a one slide review on the quantum error correction condition. So suppose we have a quantum channel with cross operators kk, and then we can design the quantum error correcting code C0, C1, which we can come up with a projection operator associated with the code space pi c. Then the condition for the existence of an error recovery channel is actually this mathematical formula, which is the cross operators, dagger cross operator, projected to these projection operators will be proportional to the projection operator. So first, there are 2 things that we need to point out. First, when you project it to the projection operator, it's not necessarily proportional to the projection operator. It can be something which is within this operator space. Within this can be like a different weighted summation of the C0 and C1. It's also within, it will also be this. So here it's actually a non-trivial statement. If it's proportional to pi c, it says the evolution in the presence of these cross operators will be indistinguishable for different code words. And in addition, these alpha jk only depends on j and k, doesn't depend on which code words that you have. And also alpha jk, based on this formula, you will see it's actually a Hermitian operator, so which means you can diagonalize it. And in the diagonal basis associated with alpha jk, you can think it as basically different errors will map your logical space to a different subspace, which is orthogonal to each other. And moreover, because this operation will still preserve the projection here. So basically, the code word, the orthogonality and the magnitude of these code words, basically the relative magnitude of the code words will still be preserved in this space. So basically, the logical space will be mapped to different orthogonal subspaces. And you can unambiguously identify these subspaces and perform recovery operation to restore the information. So, but mathematically, this is a statement for the quantum error correction condition. And now, let's actually just remind ourselves the setting. So we have the Hamiltonian, and we have the Markovian noise. And we have this master equation. And in the presence of the quantum channel, we have the cross operators, which is one is sort of dominated by identity, and the other is proportional to the Lindblad jump operator. And for the quantum error correction condition, basically we need to have our Lindblad jump operators to effectively fulfill the quantum error correction condition. To the order dt, basically we need Lj tensor identity. Here tensor identity because Lj acts on the probe space, and the identity acts on the ancilla space. So this operator will preserve the code, satisfy this condition. And when we have Lj dagger Lk, which correspond to the previously Ej dagger Ek, Kj dagger Kk, then this will also satisfy this condition. So these two conditions will correspond to the error correction condition to ensure that you can correct errors induced by these Lindblad jump operators. However, besides error correction, we also need to do sensing. So what we need is another condition, that is this Hamiltonian evolution, or the generator of the Hamiltonian, will evolve non-trivially in the code space. So basically, after the projection to the code space, it actually should not be proportional to the projection operator, so that the different logical states will evolve slightly differently, so that you can have some capability to sense the signal within the logical space. So these three conditions gives you actually the condition to achieve like a sensing. And now, once we satisfy these conditions, and I'll come back to discuss how we create these code words in the next slide. But if these conditions are satisfied, then we can obtain an effective Hamiltonian in the logical space, where the effective Hamiltonian is basically the projection of the generator tensor's identity projected to the logical space. And this is the effective Hamiltonian evolved under the logical space. And then there's only up to the negligible part associated with the dt square, which we can neglect. So now here come to the key part. What is the code word that we can design to satisfy all these three conditions? And that actually comes, that idea comes from my student Sisi Zhou. She actually constructs the code word as the following. So as I mentioned, the useful part for the generator is the part that's perpendicular to the Lindblad span. And recall that the Lindblad span contains identity in there. So if you have an operator which is perpendicular to Lindblad span, that operator should be orthogonal to identity in terms of the operator product with a trace, which means that operator times identity trace equal to 0. That means that operator itself is trace 0. So G perpendicular has 0 trace, which means the magnitude of the positive eigenvalue and the magnitude of the sum of negative eigenvalues will be the same. So we can rewrite the G perpendicular in such a way it's pull up some like normalization factors. It's actually a difference between two density operators, because the rho 0 corresponds to the sum of the positive part of the operator G perpendicular, and the rho 1 corresponds to the sum of the negative part of the density operator. And the rho 0, rho 1, they guarantee to be orthogonal because G perpendicular is also a Hermitian operator. And basically, this G perpendicular can give you two density operators of the probe. And they guarantee to have the same magnitude because this is trace 0. Then the next step is how to go from probe to ancilla. And a very common technique in quantum information is to do something called a purification. We can design a purification which is the code words, C0, C1, which is the purification of row 0 and row 1. And once you did that, you actually construct the error correction code. So let's just make sure everyone's clear on this step. So if you have a density matrix row 0, row 1, they have like a basis i's. And here it's a span over j primes. And I and j primes, they are orthogonal to each other in the probe. And then we can come up with a purification, which is a pure state spanned over probe and ancilla. And similar here. And notice that when we do the purification, there is actually a double orthogonality in here, which in the probe, they're guaranteed to be orthogonal. In the ancilla, they're also guaranteed to be orthogonal for this construction. This is actually very useful because it guarantees if you do something over the probe, the C0, C1, they will still be orthogonal to each other. And also, if you do something to ancilla only, it will also be orthogonal to each other, which gives us the distinguishability and the capability to do error correction. OK, let's look at the example that we had earlier on. If we have G perpendicular is sigma z, and the jump operator is sigma x, then the row 0 is just the 0 state. Row 1 is just the 1 state. We can do a simple purification by adding the ancilla being 0 and 1. And that's the example that we had earlier. But the general case, it could be a superposition of many terms because there is no guarantee that the row 0 is just a rank 1 matrix. It could be higher ranks. OK, so that's a construction. And with this construction, where C0, C1 are the purification of a density operator row 0, row 1 associated with the G perpendicular, then we can show the following two properties. One is C0, C1, when it's actually sandwiching any operator acting on the probe, will be 0. Because it's doubly orthogonality property. And also, C0, C1 acting on any operator and take a difference between the two, it's actually proportional to the trace of x in the product with G perpendicular. This is because the C0, C1 is a purification of this G perpendicular. And when you take a difference, it's actually effectively take the trace and you get this quantity. And recall that G perpendicular has a property that is orthogonal to the Lindblad span. So basically, if the operator x is in the Lindblad span, then this quantity is 0. If it's not it's orthogonal to the Lindblad span, then it will be non-zero. So basically, it will be able to sense the signal with some non-trivial evolution, while all the noise from the Lindblad span will have trivial effects acting on this code space. So these are the two conditions which will lead to the fulfillment of these three conditions for the quantum error correction and sensing. So that gives us the capability to do error correction and sensing at the same time. And you can check these with these examples to verify that it's true. So that basically completes the proof of the sufficient condition and give an explicit construction of a quantum error correcting code. Okay? And I should point out that actually the choice of this error correcting code is actually may not be unique. Actually, you can come up with, if you have a large enough Hilbert space, you can actually come up with many choices of code words to fulfill these three conditions. And then there is a natural question about what is the optimum choice of the code that will optimize the sensitivity. And so, and then we can actually find actually an efficient algorithm to come up, to help us to find the optimum code. So let's just see what is the kind of optimum code we want. Basically, we want to find a G tilde, which is the row 0 minus row 1, so that should be row 0 tilde minus row 1 tilde, so that this maximum trace overlap between G tilde and the G, where G is actually your probe Hamiltonian, and the G tilde is actually the thing that allows you to find the code word. And the G tilde should satisfy these constraints, being sensitive to the noise from the span, and also still bounded by this condition so that the row 0, row 1 will be density matrices. And this actually, you can find the Lagrange dual of this problem, which actually corresponds to you need to find the distance. But this time it's a slightly different distance, which is the operator norm distance, between your Hamiltonian generator and the Lindblad span. And once you find that distance, actually that distance is actually the inverse of the variance that you'll be able to sense. So this is basically like we detailed in this paper. But the key idea is that once you find this correspondence, this is actually something that you can geometrically identify, and this is something you can efficiently find by semi-definite programming. So there exists an efficient algorithm to do it. And so just some intuitive argument. If G is within this lambda span, then the distance will be 0. The distance between G and the lambda span will be 0, so there is no Heisenberg scaling because the quadratic term will have 0 coefficient. And if you have more jump operators being introduced to the system, basically it will increase the lambda span. It will increase this space, which will effectively reduce the distance between G and the space associated with lambda span. So distance gets smaller, which means the variance actually gets larger. So you get a larger uncertainty when you have more jump operators. And then there will be a sudden phase transition if the jump operator becomes so space becomes so large, then this vector will be within the lambda span, then you will never have the Heisenberg scaling. Yeah. So this is some like geometric picture that you can get. So let's look at another example, which is associated with the bosonic system. And so here, I intentionally to have my Hamiltonian to be a Kerr effect, which is quadic with respect to the creation annihilation operator. And the Lindblad jump operator will be a photon loss. And for this construction, you can easily verify that the Lindblad span, which only involve the identity, linear, and the quadratic term of these jump operators, will not span this operator. So basically guaranteed that the Hamiltonian not in Lindblad span condition is satisfied. Then we can actually come up with the error correcting code. And moreover, we can find the optimal error correcting codes if we put a bound, say, okay, the number of photons, the maximum photon is m bar, upper bound. Then the construction of the code is actually the following. So maximum is m bar, say 10 photon. I have a code C0 will be 5 photon Fock state. And my code with C1 will be a superposition of 0 and 10 photon state. And these two code words will have the same average photon number. So basically, photon loss will not induce back action to the leading order. Moreover, these two states will have a different variance associated with the photon number, which will lead to the fact that actually it will be sensitive to the Hamiltonian involution. And also, when m bar is large enough, then these actually will have a sufficient photon number difference so that losing a photon, actually there exists an error correction procedure to recover the single photon loss, which is because this coding is actually exactly the binomial code, which actually my colleagues and I constructed like a few years ago. And also recently there have been multiple experiment demonstrations using superconducting circuit. So basically this code can not only correct excitation loss, but also can be a very good coding scheme for sensing of the Kerr effect. And as I mentioned earlier, I said LIGO and error correction. And the initial motivation is that it's possible to design some error correcting codes for LIGO. But unfortunately, that may not work because in that case, we will have a Hamiltonian which is proportional to A dagger A, which is unfortunately within the Lindblad span. So basically, our results show that if the LIGO with the photon loss, which treated as the kind of this Markovian noise, then error correction will not be able to boost the sensitivity to Heisenberg scaling. Yeah, that's the sad part. But on the other hand, we have a more like necessary sufficient condition for error correction assisted sensing. Yeah. So basically, as Raphael and in his title say there's some grand unified theory, I think that there is some unification in terms of the quantum metrology and quantum error correction. Because in terms of the Heisenberg scaling, we do have some sensitivity. And from quantum Fisher information, and we can put some like lower bound about the sensitivity. On the other hand, we also have like error correction protocol, which gives us explicit construction to give us upper bound. And in terms of scaling, actually we find exactly the necessary sufficient condition to achieve Heisenberg scaling, which the necessary part is proved by quantum Fisher information, and the sufficient part is demonstrated by explicit construction of quantum error correcting codes. So in that sense, it is a unification of like the metrology and quantum error correction. Yeah. So basically, just a summary, we have this Hamiltonian not in Lindblad span is a necessary and sufficient condition for Markovian noise and and whether or not one can use error correction to achieve the Heisenberg scaling. And so there are some subtleties that we need to look into. That so far all the proofs I gave assumes that there is a finite dimensional system, because otherwise, if we have infinite dimension, I think we have a counterexample that we can actually violate this condition, which need to be verified again. And the other thing is that the relaxation of the assumptions is that if you look at the example that I gave earlier on this case, you notice that there is no ancilla. Everything is the system. There's no ancilla, but I just have the error correcting code, and I already achieved Heisenberg scaling. So one natural question is, under what condition can we achieve quantum error correction assisted sensing without ancilla? Right? And in this case, you may say, oh, yeah, it's true. Oscillator has a large enough Hilbert space which give you the flexibility to do it. But not all errors can do that. And there is some conditions that kind of needed. Because actually, when we submit the paper, we do have some critical comment from a reviewer say, yeah, you guys assume perfect ancilla, but it never exists, which is true. But the reason we do that is we want to see what's the best you can do with error correction. And for practical purposes, it will be nicer if we don't need such a perfect ancilla. We just have the system itself with large enough Hilbert space, and you can find the subspace to do error correction. So, and the other is actually, what if there's non-Markovian noise, but maybe there's some other non-trivial techniques than the spin echo that can help us to do better sensing. So, so basically, that's all I want to talk about. And finally, I would like to thank my collaborators and funding agencies for supporting this research. Thanks.